Hi there, my name is Michael Armis. This is my presentation on ATP pathways for Kin 516 Advanced Exercise Physiology. So in today's presentation, I'm going to be talking about the different ATP pathways and the way in which we generate ATP. In specific, we're going to be discussing how many ATP we yield from one molecule of glucose when we're working anaerobically, when we're working aerobically, and try and touch a little bit on beta oxidation. But the first thing we're going to talk about is what is ATP. We hear about ATP all the time. What is it? ATP stands for adenosine triphosphate. And what exactly is it? It's a really good transfer agent. Its chemical structure, which I've posted right here, it's basically one molecule of adenosine, one ribose, and that group is linked to three phosphate groups. And the three phosphate groups basically consist of phosphorus and oxygen atoms. And what ATP does is it transfers energy and raises them to a higher level, basically a higher activation level. So what is ATP used for? Basically anything and everything in the body. Certain bodily functions such as glandular secretions, digestion, tissue synthesis, circulatory system regulation, muscle activation, and nerve transmission. When we're taking a look at some of the reactions that we're going to be looking at today, for example, like exergonic reactions, this little chart that we have here just kind of talks about endergonic versus exergonic reactions. So we can talk about ATP's role in endergonic reactions, for example, when we're talking about building precursors, if you will. So an example of this could be building muscle, and ATP plays a huge role in that. Or we could be talking about exergonic reactions where an individual is working out and they're breaking down glucose, and ATP is required in order to get the energy required to keep training. So one of the things we want to talk about when we're talking about ATP, for example, is muscle actions. So for example, on a working muscle, the energy stimulates specific sites on the contractile elements of the muscle, and there's certain reactions that take place in order that ATP is actually utilized. So for example, when ATP combines with water, H2O, there's a reaction, and that leads to ADP plus organic phosphate. And so in this reaction, we get 7.3 kcals of energy. So why is this important? Because that just goes to show how much energy is created actually from the reaction of ATP and ADP combining at the same time and breaking it down. And according to McCardle, the energy from ATP hydrolysis powers all form of biological work and basically constitutes the cell's energy currency. All right, so what are we looking at right here? This is glucose, and this is an example of glycolysis right here. So this is a flow chart of glycolysis right here. So basically, if we were to take one molecule of glucose and break it down, this is how it would look like as it goes through the process as we're trying to yield ATP from this one molecule of glucose. So from glucose, we go, and it starts breaking down, we go to glucose 6-phosphate, and then we get to fructose 6-phosphate. And in those two steps, until we get to fructose 1,6-diphosphate, we're basically donating 2 ATP. So it's costing us 2 ATPs to get there. Once we get to fructose 1,6-diphosphate, glucose is breaking into 2. So it's breaking into 2 more molecules, and it's turning into glyceraldehyde 3-phosphate. I apologize about that. Once we get there, this reaction is basically happening 2 times, 1 on each side, right? And so we just went to that, and we get to 1,3-biphosphoglycerate. In the meantime, NAD has a reaction, and it gains an electron. and it ships off and it goes to electron transport chain to try and get rid of that hydrogen atom, for example. In the meantime, we get to 1,3-biphosphoglyscerate, and we get to 3-phosphoglycerate, 2-phosphoglycerate, phosphoenolpyruvate, and then we get to 2-pyruvate. In that fourth step right there where we get to 2-phosphoglycerate, we gain an ATP, and that ATP's value is 2. That ATP value is 1. I apologize. Right, and the NADH value is 2.5. So when we look at this, we're going for a jog, we start getting warmed up, we start needing some energy, right? It's not very high intensity, the demands aren't really that high, so we're working aerobically, and we're gaining some ATP as we go. And so the net value of what we get right here, just from one glucose molecule of glucose before we start getting to the other processes, is we get around 7 ATP, because this reaction is happening twice on both sides. So 2.5 times 2 on both sides, that gives us 5. Then we gain an ATP on both sides, so that puts us at 7. Now, once we get there, it's not going to be 1-pyruvate, it's going to be 2-pyruvate. And since we're working aerobically, the electron transport chain is working, and we have plenty of oxygen, and we're okay. So from there, we're going to get to 2-pyruvate, and you can see that the reaction that it could take, it could go to lactate, or it could go back to 2-pyruvate. If we were to be working anaerobically, we're working really hard, and the electron transport chain is getting backed up, then we go straight to lactate. We won't even get to the Krebs cycle because we're just backed up. All that hydrogen, it's basically accumulating and it's turning into lactate. So with this, we got 7 ATP just from this one flow chart that we have right here, and we're going to break this down as we get into 2-pyruvate in the pyruvate dehydrogenase complex right now. So once we get to pyruvate, we're going to get 2 pyruvates from one molecule of glucose. Once we get to 2-pyruvate, we need pyruvate dehydrogenase in order to get us to acetyl-CoA. And when we break down pyruvate like that, we're getting 1 NADH, which basically its value is 2.5, and that's happening twice. Once the citric acid cycle starts, this is what we're looking at right now, the entry point for the citric acid cycle is acetyl-CoA. That's the first step in the cycle. From there, it's going to move on to citrate. After that, it's going to go to aconitate, isocitrate. The step from isocitrate to oxalosuccinate is very important because here we're gaining another NADH. From there, we're going to go to oxalosuccinate. From oxalosuccinate, it's going to go to alpha-ketoglutarate. That's another important step once we get from alpha-ketoglutarate to succinyl-CoA, because we're gaining an NADH. We're also getting a GDP, and we're also getting an ATP. So there's a whole lot of energy, a whole lot of ATP that can be harvested right there. After succinyl-CoA, we're getting to succinate. After succinate, we're going to fumarate. In between that step right there, we're getting an FADH2. So there's more ATP right there. From fumarate, we're moving on to malate, where we're getting another NADH. And from malate to oxaloacetate, that's basically the exit point or the finish of the citric acid cycle. So what are the numerical values of when we're going through the citric acid cycle? We already discussed that NADH, its value is 2.5 for ATP. We see here that we get 3 NADHs in the citric acid cycle. We also gain 1 FADH, that value is 1.5. We also gain 1 ATP, we get 1 GTP. So in total, for one cycle of the citric acid cycle, we're gaining around 12 ATP. So when we're doing our ATP count, if we're working through glycolysis in an aerobic fashion, it's pretty simple. We start breaking down the ATP, and we see that during glycolysis, in the first step, we have 2 NADH. So that gives us a value of 5 because there's 2 of them. Once we get to the pyruvate dehydrogenase complex and combine that with the citric acid cycle, we start counting all of our NADHs up. So we have 8 in total there. 8 times their value of 2.5, that gives us 20. we get two FADH2s, and their value is 1.5. There's two of them, so that gives us a total of 3. From each time that we are in the citric acid cycle, we get 1 GTP, but since it's happening twice, we get 2. And then also we have 2 ATP that we gain from each citric acid cycle, so that gives us 2. So that gives us a grand total of 32 ATP when we're working aerobically through glycolysis. So earlier we talked about glycolysis, and now during glycolysis we talked about when we're working aerobically, briefly touched upon the electron transport chain. What's inside the electron transport chain? So there are cytochromes that are located inside the electron transport chain, and the cytochromes are basically a series of iron, protein, electron carriers located on the inner membranes of the mitochondria. The electron transport chain is very important because during oxidation, hydrogen atoms basically are released by dehydrogenase enzymes from nutrient substrates, right? And so in the electron transport chain, the electron transport chain is used to pass on electrons carried on by NAD and FAD, hence the NADH, FADH. And by settling the electrons out, they reduce oxygen to form water. So basically, when you're working aerobically and you're moving around and your NAD and FAD is carrying those electrons to the electron transport chain and coming back, they are accepting those hydrogen atoms. If you start working hard and you start picking up the intensity, you start doing sprints, basically the electron transport chain gets backed up and the hydrogen atoms get so backed up that they can't be processed anymore, and you are not working aerobically anymore, and so then you begin to just create lactate, and you do not go through the Krebs cycle or the citric acid cycle. You are not doing beta oxidation, and so the electron transport chain is extremely important in when performing aerobic glycolysis. So now we're going to be discussing a little bit beta oxidation. And what we're going to be doing is discussing how during beta oxidation, we're going to be breaking down one molecule of fat and counting the ATP that we gain from that. So basically during beta oxidation, there is a NADH and FADH2 that's produced, and that's turned into a 2-carbon acyl fragment. Basically, beta oxidation kind of works hand in hand with the ETC and the and the Krebs cycle, or the citric acid cycle. And so it's basically each time a fatty acid undergoes oxidation, we shorten it by 2 carbon atoms and produce one NAD and one FAD. And so then in doing so, we can use beta oxidation when you are exercising for a very long time. So basically you start kicking in, you start using fat as a resource. For example, you see this a lot with marathon runners. They deplete their glycogen stores and they're really struggling. And so basically fat starts coming into play and becomes the main energy source when you're doing long, intense exercise durations and your glycogen stores are depleted. Basically, athletes or individuals who are highly trained, based off their nutritional status, their level of training, and their intensity, goes hand in hand with the duration. And basically, you can become more efficient at burning fat and using fat as a resource. Also, there's possible enzymatic adaptations that can come along with being proficient in this way. So with a diet that consists of high fat and low carbohydrates, you can enhance your fat burning capabilities or fat oxidation capacity. And so when we're looking at one carbon fatty acid molecule, we're looking at 147 molecules of ADP, and then that is phosphorylated into ATP. Each triglyceride molecule forms 441 ATP. So basically, this can constitute anywhere from 30 to 80% of the total energy that is manufactured by the body that we can actually use as a resource to perform anything that we're looking to do. So here we have a flow chart of beta oxidation, and as we can see, as fatty acids, a chain of fatty acids, a chain of 3 fatty acids can actually enter beta oxidation, and as you can see here through the cycle, we get coenzyme A. We're producing hydrogen that's shipped out to the electron transport chain, and we're actually producing a 2-carbon acyl group that gets shipped over to the citric acid cycle that could then go into the Krebs cycle or citric acid cycle and help produce more ATP. With beta oxidation, we can also combine that with glycerol, and glycerol can actually enter glycolysis without actually having been converted into glucose, and therefore can be recycled for energy. So when we're looking at counting ATP through beta oxidation, we can see that 1 molecule of glycerol is equal to 19 ATP. We can also see that 3 molecules of an 18-carbon fatty acid chain is equal to 441 ATP. Or if you prefer, 1 molecule would be equal to 147 ATP. So in total, from 1 molecule of glycerol and 3 molecules of an 18 carbon fatty acid chain, we get a total of 460 ATP from beta oxidation. My name is Michael Armas. This has been my presentation on ATP pathways. Thank you very much.